on after the coffee break. So second speaker of the day is Charles Cox from Bristol University. And even though it says the spread of infinite groups, I have a feeling that he will be talking about Houghton groups.
Yeah, I will. This is based on a paper that's on the archive. It only came out end of December. So it's quite new things, and there will be some opportunities for like little interactive parts, because I think it's nice to be able to interact with people at the moment. And do feel free to post questions in the chat, or I mean, I'm sure Mikhail will be confident enough to keep his mic and heckle me with things. So do feel free to ask as we go. So
always a pleasure to heckle you.
So it's a pleasure to be here to be heckled, which is nice. Right, so what is the overall scheme of things we're doing before I tell you some of the things on the slides that I've got pre-prepared? So the idea is, as a group theorist, it's good to have interesting questions, and I was surprised because there's lots of pretty interesting generation type questions that finite group theorists have asked, but we haven't really asked these questions for infinite groups. And so this is sort of one such question. And I mean, at the end, I can tell you some others, but some other work has been on some of these other questions. A few of them have been raised by Weigold in sort of the 1970s. But I think they are genuinely interesting questions. And some of the results for finite groups are really interesting. So after this first page, there won't be any finite groups, but it's kind of saying what is it we can say about the infinite world that we said about the finite world. So the notion we have is spread. We're going to be talking about the spread for infinite groups. So this is a notion studied for finite groups quite extensively. So what is it? Well, we talk about spread n, and that means you give me n elements in the group. You give me any n elements you like, as long as they're not trivial, as long as they're not the identity element. And I can find something that generates with all of those n elements at once. So obviously we need the group to be 2 generated, because otherwise you're not going to be able to find such an H. And I don't want an isomorphic copy. I really want the whole group. You could actually ask for an isomorphic copy when we're working with infinite groups, but this is a definition that was introduced for finite groups. And well, what do we have as a first sort of little observation? Well, this is the lemma we have. So if you've got a normal subgroup that is non-trivial, and you've got a non-cyclic quotient, I need to say, don't I? Then the spread is 0. So we say the max of all such n, or the supremum, if you like, is denoted by the spread of G. So this is going to denote the spread of G throughout. So this, having spread at least 1, so having positive spread, is a property called 3/2 generation, because somehow it's stronger than being 2 generated. Yeah, it's stronger than being 2 generated, but it's weaker than being 1 generated. So cyclic groups immediately are going to satisfy this. But this lemma here really reduces the groups we can look at. So how do we prove it? Well, if you pick your element here to be in the normal subgroup, and then you're done. That's like literally it. So you pick your element G1. Well, then if you pick any H at all, then G1 with H, when we're then in the normal subgroup, this is at best going to be cyclic, because it's generated by H. So it can't be the whole group, because that quotient isn't cyclic. So this is just one of those initial observations you can make, very simple observation, but it kind of tells us a limiting property about what groups to look at. And so throughout this whole talk, I'm going to call this condition, so that every proper quotient of the group is cyclic, I'm gonna call that condition star. So first thing is that you might wonder for finite groups, because I said I'm going to talk about finite groups in the first slide and then stop talking about finite groups. But for finite groups, every finite symbol group happens to be 2 generated. So it makes sense to say, what's the spread of a finite group? And for finite simple groups, they all actually have positive spread for finite simple groups. So there's a paper by Feigold for all the alternating groups, and you can show that all of these have spread, at least one. But surprisingly, this lemma, this one small condition about that, obviously it includes the class of simple groups, but it includes anything where every proper quotient is cyclic, that actually completely characterizes by the work of an enormous number of people. I can't list them all in that one box, but for finite groups, this actually completely categorizes groups with spread at least 1. So it's a true statement due to many, many theorems and lots of work by lots of people. And I can't name them all here, so I'm sorry that I didn't name them all. But that if you give me a finite group and every proper quotient is cyclic, then it has spread at least 1. So that's kind of an interesting statement to make. It's a surprising statement about generation that we can say for finite groups. And the other thing we can say for finite groups, which is also in a paper called The Spread of a Finite Group, which involves some of these authors above, and that is that you can't find a finite group with spread exactly 1. So if you have spread 1, then you have spread 2. That's their statement. Okay, so there's nothing in this definition that stops us from asking this question for infinite groups. In fact, most infinite groups that people will think of are probably 2 generated. And then you can ask, well, this lemma up here, this lemma we've already covered, there's nothing wrong with that argument when working for infinite groups. So what can we say for infinite groups? So it's worth having some examples. And this is first interactive part. So what infinite groups do we know? You can feel free to type in the chat. You can call out if you're feeling confident enough. What do we know? What are some examples of infinite groups? This is where finite groups end as well. There won't be any more finite groups.
That's the obvious one.
Sorry, which one? The
Z.
set?
The integers.
Oh, the integers. Yeah, okay. Let's do the integers. And we might as well generalize that with Francois' talk. We might as well talk about the free group of rank n more generally. Because we've got Alejandro here, we might as well put branch groups on here. And I think I'm correct in what I'm about to do. Alejandro can correct me for what follows. Any other groups? Do we know any other groups? There we go. Somebody said Thompson's groups, which is great. So Thompson's groups. Anything else that we know?
I think we should have Houghton's groups.
Oh, we should, yeah, there we go. They are actually all subgroups of Thompson's group V. But whether some of these properties are preserved by finite index subgroups or by subgroups is sometimes not known. So anything else?
ESL.
Oh, PSL. This is where I'm not sure. I think that goes here. Yeah, I'm pretty sure. Do you want NZ? I'll explain what the 2 columns are in a second. Anything? Oh, the lamplighter group. Excellent. Yeah, let's put that over here. And more generally, let's do A Reith Z for A finite abelian. Okay. I don't know if anybody's worked out what I'm doing yet, what the 2 columns are going to mean, but at the moment, you've not got the best of hints. But okay, so this I think we've got enough groups there. I mean, I'm trying to think what else I was expecting. Any other last takers? Anyway, if you come up with something, I can always add it there. So
We have Tarski monsters.
Wonderful example. I don't know the answer though. Yes, they're over here. I think they're a good example. Thank you for asking about. So hopefully, I think all the things on the left are residually finite. I know some branch groups are. I'm not sure whether they all are. So do they need to go here as well? Yeah, okay. When I saw you, I thought I better look up branch groups, and I could see some of them are residually finite, but I wasn't sure about all of them. So I suppose the point of this is that many people study Thompson's groups, and they're a good example of something that's not residually finite. But most of the groups we think of are probably residually finite. So let me tell you what that means, residually finite. So it means that you've got lots of finite quotients. Okay, that's a good one as well. Yes. So some of those are is it open about residual finite? I mean, nobody said hyperbolic groups either, which would be harder. But if
yeah, I mean, it's understood completely when they are residually finite, but
yeah, that's
so,
when one of the numbers is 1.
So can I put? I'm trying to think what they look like. So over here, I can do this, can I?
Yeah.
I have people shaking their heads or nodding their heads. Good. Okay, so
the Tarski monsters I've heard of are infinite simple groups.
Okay, yes. So they can go. This is where it's useful to give an online talk, because I can just cheat. So they can go there if we want. I mean, I'm trying to think exactly how that matches with what I'm about to say. Anyway, okay, maybe they go over. I'm going to put them here because I'm unsure, but they're a good example. I think by what I'm about to say, they're not infinite simple. I'll have to think about that in a bit. Okay, so residually finite. That means that you can for every element in the group, you can realize that element in a finite quotient. Okay, so most people are probably happy with this. I mean, most people know at least one of the groups above better than I do. So residual finiteness, that's a very key property. But what can we say about all the groups above? If they're residually finite and they're infinite, and they have this property star, so that's every quotient, every proper quotient is cyclic. They are simple, are they? I'll have to think about that with Tarski monsters, because Tarski monsters I will talk about in a bit. Then what do we know? Well, then actually G equals Z. So this really limits our choice of groups. So if your group is residually finite, basically we're not interested in it for this property. So let's prove this, because it's almost as easy as that first lemma. So the first thing is, so point 1 is G is abelian. So if you're residually finite, okay, yeah, so Tarski monsters are going to go over here. It is early here. Right, so if you're residually finite, then we can do the standard trick. You can pick a commutator that's not equal. So assume not. So you pick a commutator that's non-trivial, then there exists n finite index in G, such that this contains a commutator of AB, which is non-trivial. And then by star, this means this quotient is not cyclic, because it's not abelian. Okay. So that's the first thing. So it's abelian. G has to be finitely generated. Well, you just pick then it's abelian, remember? So G so by star, this is going to be cyclic. So it's generated by some X. Take the pre-image, well, then it's 2 generated. Okay, so it's finitely generated. And now you've got a finitely generated abelian group. And we know exactly what these look like. Just by property star again, what are the quotients got to look like? It's got to be infinite, so n can't be 0. If n's 2 or more, then we break condition star. So you get n equals 1, and then a has to be trivial. So the only way we can look at residually finite groups is if G equals Z, which tells us the Tarski monsters are not residually finite. Okay, so some questions. What if we take this condition star? Does the theorem for finite groups that says if you have condition star, so if you have every quotient, every proper quotient is cyclic, then do you have positive spread? And the answer is, well, this is not a properly phrased question yet. Because, for example, if you take alt X, let's actually pick Z. So the even permutations with finite support. And here, the support of an element G, exactly as in Francois' talk, at the set of X, such that they're moved by G. So this alt Z is an infinite group. It has condition star because it's simple, but it's not 2 generated. Now, there actually exist 3 generated groups that are simple, so they also break it. So this is not a good question at the moment, but we can modify our question. So just say, given G, a 2 generated group star is the spread of G bigger than 0. Okay. So maybe you've got your favorite group and you can think, is it going to be a sort of a counterexample? Can I find a 2 generated group where every quotient is cyclic, every proper quotient is cyclic, but it has spread 0? So in the if you look for finite groups, then that's not going to work. So partial answer, if you're residually finite, then you're either finite or you're Z by the above lemma. So it's not worth looking for a counterexample to Q1 dash if you look at a residually finite group. So we need to look, let's Q1 dash. We need for this particular question, which was asked in the paper I'm going to show below, there's no point in looking at residually finite groups. And that's a very large class of groups. It's a it's got many well understood families in it. So that's why we're going to use Houghton's groups, because they're not residually finite. So the other questions that are very natural to ask are, can you find a group where the spread is exactly 1? And can you find one where it's infinite? And this is where we've got 3 answers at the moment. So all of these questions come from Donovan Harper. So Scott Harper's at Bristol at the moment, and Casey Donovan, and he wrote a paper called Infinite 3 half-generated groups. So it's saying that the Higman-Thompson and the Bryn-Thompson groups all have spread at least 1. So that's what they show in that paper. So for the Thompson groups, that was the only result that was known, was about the Thompson groups, and then about these sort of quite easy to see, these 3. So C2 is because we didn't say that the elements G1 to Gn had to be distinct. So just sort of by a definition, you get the cyclic group of order 2. Z, well, yeah, you can just always pick the generator, so you're done. And tasking monsters is a similar thing. You just, given any element, it's going to generate a prime order proper subgroup, and then pick some element not in that subgroup, and you generate with it. Okay. So are there any others?
What about the infinite cyclic Tarski monster?
Is there an infinite cyclic Tarski monster?
Yes, there is.
There is. Yeah, well, I don't know. This is where talking to people who know things about infinite groups, you can ask later if you want, Mikhail. Otherwise, you're going to like really derail the talk because I won't get through everything.
The
Oh,
same
I
would
don't know.
apply, I think. You just pick some generator outside the cyclic subgroup.
Yeah, well, that generates everything.
Yeah, and that's going to generate everything. Yeah. So Houghton's groups, how to think about them? Let's give you the definition of these groups. So quite a natural question is, what's the limit of the group's SN? I feel as though I'm mentioning finite groups here, but since I'm talking about a limit, maybe I'm not. So answers, some people would say it's Thompson's V. Some people would say this. Some people would maybe say it's the group we had before, it's Alt Z, or it's maybe F sim Z, or it's maybe sim Z, and I'll explain what each of these are. So this was all even permutations. This is all elements of finite support. Then this is very naturally, this F sim is very naturally the limit of all the symmetric groups, because it's just like the union of all of them. Sim Z is all permutations Z. So this is an uncountable group. The F sim Z is countably generated. It's not finitely generated. You can generate it with all the 2 cycles, for example. But I'm going to claim for this talk that Houghton's group, H2, is a natural way of thinking of this. So S this is a very natural generating set for S2n plus 1. What does this generating set do as n tends to infinity? Well, you can think that this part here maybe tends to T, which sends Z to Z plus 1 for all Z in Z. And then you've got the permutation 1, 2 still. So you've got a copy of Z. What does this group look like? Well, if you give me an element in F sim, so if you give me something in here, then I can actually build it in this group. So let's write down T1, 2. So this group contains F sim Z. And why is that? Well, it's because anything in F sim Z lives in some Sn, and I can build every 2 cycle using T and 1, 2, because I can conjugate the 1, 2, and then I can build every 2 cycle using those 2 cycles. And I have a terrible joke for you, which is, I mean, I think every dad, maybe, I don't know, I'm not a dad, but every dad probably has the joke in the UK that says, this is it in the UK and this is it in Australia. So since I'm giving a talk to Australians, you can think of Z really as 2 copies of the natural numbers. And then let's draw this a bit bigger. And then you can say, well, this is Houghton's group. Let's do it this way. This is Houghton's group in the UK. And this is Houghton's group in Australia. And why am I telling you that? Terrible joke. The reason is very simple, which is that element that we've just done is not in Houghton's group, but it is. So what does the automorphism group of Houghton's group look like? So it looks like HN is centerless, so you get conjugation by elements of HN give you automorphisms. And then what else do you need? Well, the only other thing you can do is these isometric permutation of the rays. So doing that sort of thing. So in this case, you've got 2 copies of the natural numbers. That's being seen as Z. So if you like, the transformation that sends X to minus X for all X in Z is the only element you then need for the whole automorphism group, other than conjugation by elements of HN. Right, so what are some properties about these? So they are eventually a translation. So what do I mean by that? Well, I mean that actually this is looking like, I said it's got fsim Z in it. And that actually is normal. You can see it's normal because it consists of all the torsion elements. And this is a semi-direct product with the element T. And that means if we look at an element, then it looks like sigma T to the K, or let's use another letter, the D, where D is in Z and sigma is in fsim Z. And that means we can really understand what the orbit structure looks like. So the orbit structure, eventually, if we go far enough away from the origin, we are just seeing this part. So that's translating by D. And then if we go far enough away on this side, we're translating by minus D. And so if we look at the orbit of this point, it's going to go off to infinity this way. And if we look at the orbit the other way, then it will hit some infinite orbit on this other side. So this is what elements look like. They maybe do something crazy in the middle, and they have any finite permutation you like in the middle, but eventually they're acting as a translation. And that's one way to define them. They're the permutation groups that are eventually acting as a translation on n copies of the natural numbers. So this is H2. This is this group. Why am I spending so much time with H2? Well, the whole talk is now going to be on certain finite index subgroups of H2. So that's why I'm introducing this group quite carefully. So what are some properties of this group as well? So it has exponential growth. And how do you see that? Well, if you look at, let's do it this way, 1, 2, t squared, then that is the Lamplighter group, and that has exponential growth. It actually contains, so it has exponential conjugacy growth as well. That's a result of Sapir. It contains F wreath H2. F wreath H2, and that's basically the same argument as here, because it's got lots of copies of H2 within it. So it's got this kind of strange property with that. It's elementary amenable. It's one of the main things it was studied with respect to is that it has this, each Houghton group Hn is Fn minus 1, but not Fpn, where these are finiteness conditions that I don't actually know very much about. It has solvable word problem, conjugacy problem, twisted conjugacy problem. So it's quite nice as far as sort of decision problems go. And it's also highly transitive in the sense of Francois in his talk said about. So given that, one way of saying that is that it's K transitive for all K in the natural, for any set of K elements. And that's because it contains fsim. So Osin has a paper called Highly Transitive Groups, and what's it called? And Mixed Identity Free, I think. Or maybe it's just called On Highly Transitive Groups. But he's got a paper, and in that he shows, you just, given any group, you can quite easily put fsim into that group. And if you do that construction, Hull and Osin, yeah, thank you. If you do that construction with Z, then what you get is H2. So Z is in some way like the most obvious group to start with, And if you do that construction, then what you get is H2. And you actually get this exact generating set, basically. Right. Other things to talk about. So I'm now going to define this group here. So GK, this is, I'm saying it's finite index. I mean, you kind of check that. For each K in the naturals, this is a subgroup of H2. Okay. So there's nothing that complicated about what's going on. I mean, I don't want H2. So H2 doesn't have star. And that's because if you do H2 and you quotient out by alt Z, then you get C2 times Z. So I could instead use like G1, which is alt Z with T. And then naturally, so if you like, G1 equals 1, 2, 3, T. So that happens to be 2 generated, but I can put any power I like. And so second, see if everyone's kind of still awake, whatever time it is where you are, whether you start drinking. How this is finitely generated, because I've said it's finite index subgroup of H2, but how many generators do we think we need for a general GK? Maybe type in the chat, maybe have a think, like what do we need? So I suppose one real brute force way would be, you kind of got these blocks and each one is a copy of AK, the alternating group on K letters. And then you've got this T to the K. So maybe you need, and that's a way to see it's finitely generated. You need AK plus 1, because you probably want to be able to do something with these blocks, and then the T to the K element. I don't know, have a think, how many elements do you think you need? And so this is the first observation, is that you can actually generate it with this many elements. That's quite a lot of elements. But A2K plus 1, so when I did this, I didn't have this intermediate step, but GK can actually be generated as well by, well, A2K plus 1, that equals that's generated by these two. So that's 2 generated. So we can replace this thing with 2 elements. So that means we're now 3 generated. But can you actually be 2 generated? And the answer is you always can be. So I'll show you a 2-element generating set for any GK. I don't know whether people are in disbelief or not. So I didn't really believe this when I wrote it down, but I think from the above statement, it's a bit more obvious that it could be 2 generated. So what can we do? Well, we want to generate A2K. So I'm going to take blocks of size 2K on Z. Okay. And I can use any element. I'm going to use T to the K, and I'm going to use alpha, where alpha is some element in alt Z. So alpha has to have finite support, but I can make it as big as I like the support. So I'm going to make this as big as I like. Now what I can do is I can enumerate omega 1 to omega n, the 3 cycles. This is kind of 1 in A2K. Now, if I pick K big enough, A2K is generated by the 3 cycles. And I can conjugate all of the 3 cycles. They're all conjugate to 1, 2, 3. So this tells me if I now put like sigma 1 here, sigma 2 here, sigma 3 here. So its support is contained in each box, each block, if you like. This tells me that this element together with 1, 2, 3 and T to the K is definitely going to generate, because I can take my 1, 2, 3. I can take my 1, 2, 3 I can conjugate this big block here, this big thing here, to move it over the 1, 2, 3. I can do that with t to the k, and then I can conjugate 1, 2, 3 to any 3 cycle I like. And now all you need is you need to work out how to make 1, 2, 3. So the way we do that is we now put one thing at the top and one thing at the bottom, such that if we do the following trick, so if you like, maybe this is the best way, but so that the top block, the bottom block, if we take the commutator of these elements, so this is alpha, it's made of lots of blocks. This is alpha, but conjugated by some massive power, so that this block hangs over this block. Then if I take the I can choose this sigma 0 and sigma n plus 1. I can choose that so that the commutator of these two then gives us the element 1, 2, 3. Right. So these are actually 2 generated, right? So every GK, so the take home, every GK is, so naturals is 2 generated, which I thought was quite surprising. I mean, I wasn't expecting to find all of these groups, and they're all finite index in H2. So why have I done this? Well, just have a think now. G4, that looks like sigma t to the 4, any element in there. Oh, I shouldn't use. Oh yeah, that's a 4, not okay. Yeah. So it has elements that look like that. Now, the eventual orbit of this is that eventually it has 4 infinite orbits. Well, it has 4 infinite orbits, and then it has stuff going on in the middle. So the key thing to think now is, well, how can, if I'm working in G4, how can I pick an element that generates with 1, 2, 3? And the point is, you can't. Let's do it like this. It's also worth, I mean, these look like Alt Z. Right. K. That's what GK looks like. So they do have the property on quotients that we wanted. So these are 2 generated groups with every proper quotient is cyclic, because every normal subgroup happens to contain Alt Z. But we've answered our question because they do have spread 0. So the proof is just take 1, 2, 3. That can't generate with anything. So in order to generate with something in G4, you need to pick something that has 4 infinite orbits, but because otherwise you can't generate the t to the 4 part. But then you're not going to be able to do that, because something with 4 infinite orbits, only those infinite orbits, each of them, if it intersects one of these, you've got 1 infinite orbit left over. And so the group we've produced can't act transitively on Z, can't act K transitively, because it's 1 infinite orbit is just being moved by the other element we've picked. Okay, so these were quite easy to define, right? I mean, there's not anything that complicated going on as to what we've defined. I started some of this work in May and wrote a couple of other things. So I mean, it's not a huge body of work. It's just a 12-page paper or something. And the main other work in the paper is something that I want to talk about at the time I've got at the end. I suppose any questions before I move on, because I've made that proof quite brief. Feel free to. Why have I got so much space? Was I going to say anything else at this point? I'll let people think if they have any questions. I'll just check I've not got anything else that I was supposed to talk about. Okay, right. So the other parts of the talk now are going to be to say about the groups G1 and G2. So that as well, the K equals 3 cases, slightly different, but it's not significantly more different. Basically, when you use this element 1, 2, 3 with the K equals 3 case, you end up generating something that looks like C3 reset. That's the best you can kind of do. And then that obviously isn't the whole group. So, I mean, I'm not going to go into the details here. The point is that most of the groups in this family are break this theorem that held for finite groups. So what about G1 and G2? So that, let me just write down what they are again. So maybe they have infinite spread, these groups. Be nice if they did, right? So it turns out in here, if we let Sk be equal to let that equal this element, then you can, if you give me an element, oh, I shouldn't really be using K. I like the letters K too much. So given is true. But moreover, if we're given G1 to Gn, then there's one that there's a K large enough such that this generates with all of them. So this is maybe evidence that they might have infinite spread. Similarly, if you're given an element in alt Z, then you can find something that generates with it. So what's that statement? I can say it actually for every group GK. So given any n elements, there's something that generates with all of them, as long as you don't pick something in alt Z. And alt Z is very small in this group. Right? So what's a generating graph and what does this tell us about it? So generating graphs, another thing from finite group theory. So you've got a graph gamma. V of gamma, I'm going to define as G about 1. So it's non-trivial elements. Oh, didn't know I could do that. And the edge set of gamma, I'm going to connect two elements if they generate the group. Right. So you can draw these things for finite groups, and spread tells you something about the what's it called? The diameter of these graphs. So this proposition really tells us quite a strong condition on the generating graph, because it tells us that if we take any elements not in fsim, if you think about the ball of radius n, so you think about it as a Cayley graph, then if you take the ball of radius n, then every element in there that's not in alt z connects to one of these SKs from above. So there's, in the conjugacy class of just T, that's generating with basically everything in the ball of radius n, because alt z is quite small in there. Right, and then I've got another question to see if people are. Oh yeah, okay. I've got this, which I might, yeah. So in order to show how to do it, a 3 cycle, when does that generate with? So if I give you an element ABC, when does that generate with T? So when does that actually happen? Basically, the only thing that goes wrong, so if we pick something like this doesn't equal G1. And the thing that we do is if we pick this equals G1 if and only if. So if we got A, B in the naturals, then it generates if and only if their greatest common divisor is 1. And that's because we just do the Euclidean algorithm. So we just have these, this is A away from 0, this is B away. And we just conjugate it so to reduce until we get down to -1, 0, 1. And how is it we generate? So it's easy to determine this. And then how do we reduce to the case where you're a 3 cycle? Well, you imagine you've got sigma, and it's a similar trick to what we did before. So you conjugate sigma by, so we're really thinking, yeah, okay, this is the best way to say it. So we conjugate sigma by some power of t. We make it so that their supports overlap by 1. We then conjugate, let's call this alpha. So then we take sigma inverse, cool. Take this. And that looks like the element we had before, but changed by exactly wherever this sent. So instead of this point, it's some finite tree permutation, but then it goes out to that point and then goes back in. And let's call that beta. And then if we do the right combination of these, I think it's something like this. The other way I think will work as well. This gives us a 3 cycle. So if you want to generate with T, then this is how you do it. But there's not a big problem as to what's going on, because all we're doing is we're saying, if you want to know, if you've got an element sigma and you want to generate with T, then instead of generating with T, well, we're going to pick something in the conjugacy class of T, but then this is really the same as this. So we can just change the ordering and work with T. And if we pick the correct ordering, we can force this condition above, this one here, to hold. And so then we can always generate with 1. I'm not sure if I've really got long enough to do the last bit, but I can maybe ask what people think. I've not got quite as many people here as enough to vote. But what do we think? Do we think based on what we've seen, do we think it's over here, that maybe both of them are finite, or both of them are infinite, or that one of them's infinite and one of them's not? So given the strength, just before I let people vote, given the strength of this statement, so this is saying it's infinite as long as you don't pick things in alt Z. And it's a very short argument. This is actually a very short argument. And then you can do it for h in t to the k. So this is a very short argument. So maybe we can generalize it. The argument for G1 for generating with an element of alt is really quite easy. So what do we think?
My personal guess is that G1 is infinite and G2 is finite.
Okay. So what I could, if I had more people, I suppose I can let you. Yeah, I'll let you. You can annotate if you want. So Mikhail said this and this, right? So you can annotate, but I am running slightly down on time. So I thought both would maybe be infinite. And with the G1 case, if you pick your G1, so if you pick your elements and then you pick some other ones, and the other ones are in G1 without Alt Z, you can basically modify the choice you made here to work with the rest of them. So you only really have to worry about generating with n elements that are in Alt Z. And if you pick each one where GI has, where the support of GI contains something new that wasn't in the previous ones, then you can do this. But it turns out that the answers are, oh, let's do it like this, are that this is finite and that this is finite. So thank you, Mikhail, for having a guess. It was a good guess.
Right.
Yeah. I mean, yeah, so the average number of correct by random guessing. So one right, one wrong. So they are both finite, and I'm going to end just by, I mean, you can also show both of these, and this is much more difficult than I thought it was going to be. This is actually really quite, it's like a page and a half to prove this. It's very easy actually to prove that it's bigger than or equal to 1, but to prove you can generate with 2 elements of Alt Z was surprisingly intricate. So as a very last thing, these are short arguments to show that, in fact, the spread for each of these groups is finite. So how do we do this one? This is the easier, which is why we kind of get a smaller lower bound. These are not ideal lower bounds. So how do we do this? Well, this one, we want to show that if you pick 10, I can pick 10 elements, G1 to G10, such that no element of G2 generates with all of them. And that's what we want to show. So first thing we kind of use is that maybe we should pick all 3 cycles, because 3 cycles are easier to work with. And maybe we should pick all of them having support contained in the same set. So I'm going to use 3 cycles with support contained in this set. I'm just going to note that to generate with a 3 cycle, we need to look like sigma t squared or sigma t to the -2. And up to changing it for its inverse, we can imagine we look like this. Now, such an element has 2 infinite orbits. Then we can say, well, what can we do with these 5 points? They either lie on the first infinite orbit, the second infinite orbit, or on some finite orbit. Now, let's imagine that 2 of them lay on a finite orbit. Well, if 2 of them did that, then we can, and it's these 2, then we can pick 1, 2, 3, and that's not going to be able to generate with this element, because you're only hitting 1 of the infinite orbits. So at most, we can have 1 finite orbit. And then similarly, if you had 3 points that are all on the same infinite orbit, you can do the same sort of thing, really. I mean, you can just pick 2, 3, 4, and that's not going to work. So at most, 2 can lie on the first infinite orbit of this element. And then I should really use different colors, shouldn't I? And then we've got 2 like this. This causes a problem, because now what I can do is I can pick these 3 points. They're not going to work. So if I pick all 3 cycles with support contained in 1 to 5, and then I throw away the inverses, because I don't need both the element and its inverse, then this gives us 10 elements. And you can't find an element that generates with all of them. For the other one, the other one's slightly neater in some sense. So you can't do something with the infinite orbits in the same way, I don't think. But you can say, imagine you've got 5 points. You've got 1, 2, 3, 4, 5. Well, imagine they're all on the infinite orbit of the element that you're trying to generate with. We're going to again use 3 cycles. If these distances are A, B, C, and D, you break the greatest common divisor condition, because you can show that if say B was even, then whatever choice of odd or even for the other numbers, you can combine them. So if B is even, that's like saying 2, 3, the distance between those is even. And then you end up being able to break that the other ones will also be even. So this is like even, and you get this is even. And then that won't generate with with T. So the details are all in the paper, but these arguments actually weren't as bad to write down once you just think, well, I need to use some 3 cycles. I'm going to just use alt. And just to sort of end on the questions. So question 1, the answer is yes. And we've got infinitely many examples. This one, well, we don't know because we managed to show both of them have spread bigger than or equal to 2. And this one, other than the examples of the Tarski monster and of Z, well, we don't know yet. So it's not known with the Thompson groups whether they do either of these 2 things. And that's about the end of the paper, and about the end of the talk. So thank you for listening. Thank you for the clap.
Yeah, thank you for the talk, Charles. Do we have any questions? Well, doesn't seem like it. So
yeah, maybe just I had a question just about these 2 examples that you just explained. Do you have any conjecture for the exact S of G1 and S of G2?
No. So the reason for showing that they're bigger than or equal to 2 is just because of this question of saying, are they equal to 1? And G2, it was so difficult to show that it's at least 2. You'd have to then show given any 3 elements of alt Z. And that seems nasty. I think with what goes on with G1, you could probably show it's strictly bigger than 2. But with the upper bounds being so big as well, I don't want to like reduce and reduce. If I had to guess, I'd maybe say that I wouldn't be surprised if this were actually 2.
Okay.
But for the other one, I think there's some results about odd, the alternating groups on an odd number of letters and the spread of these. So there's the fact that these are kind of the infinite analogues of those. I was thinking that it would maybe be infinite, but no, we've got a finite bound. Yeah, and the bounds are not ideal. They're just to show that it's not infinite. But yeah, it's a good question. I mean, maybe this is maybe SG of 2 is 2, but I mean, yeah, it's fiddly to do any more than 2. But yeah. And,
Okay, thanks.
any further questions for Charles? And if not, let's thank him one more time.
Thanks.
And yeah, thanks, Charles. It was a nice talk, and hopefully we'll meet again for another seminar soon. Bye, everyone.
I suppose if anybody wants to ask questions, then stick around. But it's late.
Okay, then I have a bonus question for you. I mean, it looks like this could be also a question you could ask about some topological groups, but then you just want to generate a dense subgroup in your group. So I was wondering what happens, like if you say you take the whole permutation group of the integers. Yeah.
So do you want to take F sim Z or do you want to take sim Z?
No, really the whole symmetric group.
So sim Z, the uncountable.
Yes.
Yeah.
But now you want to ask just to generate a dense subgroup.
I suppose the only thing, I don't know very much about topological generation, but the only time it's come up is there's another generation property that finite group theorists are interested in, which is called invariable generation. And that says, if you're given, can you give me a set, which if I take any conjugates of the elements of that set, then it still generates the group. And people have studied this for topological generation. And there are some strong results about topological generation. And people have also studied this for infinite groups. So yeah, topological generation definitely has been studied for this sort of question.
Yeah, I know for pro-finite groups, there's people looking at positive finite generation. So you pick like n elements at random, and there's a positive probability that generates the group. So I guess for Polish groups, there may be some kind of like generic generation type questions.
Yes. There are.
Yeah, so there's really nice results about SN for the random generations.
Yeah, so if I recall correctly, the free pro P group on 2 generators is positively finitely generated, but the free pro finite group isn't.
That was quite a recent paper, I think, was it?
No, I think it was from a while ago.
Oh,
But yeah, it comes down to sort of the growth of the quotients, I think.
I can stop sharing if you want, Mikhail.
Yeah, well, I'll stop recording now.